Fine. Let's start. Number 10. The central singularity. Here's the answer you already know. You fall past the edge of a black hole, and everything you are gets crushed down, smaller and smaller, until it reaches a single point of infinite density, where space and time simply stop making sense. That's the picture from the textbooks. That's the picture from the documentaries. A dot at the center, where the math screams and physics ends. And for a long time, that wasn't even taken seriously as a real prediction. People assumed the singularity was a cheat, an artifact of pretending stars are perfect spheres. Real stars are lumpy. Real collapse is messy. Surely all that mess would swirl and miss, and never actually converge on one perfect point. Then, in 1965, a 30-something mathematician named Roger Penrose sat down and proved otherwise. His paper was barely 3 pages long, and what it showed was brutal in its simplicity. You don't need symmetry. You don't need the star to be neat. Once a collapse passes a certain threshold, once you've formed what he called a trapped surface, the singularity is unavoidable. Not likely. Unavoidable. Baked into general relativity itself. That single result is often called the second most important contribution to gravity after Einstein. Penrose won half the Nobel Prize for it in 2020, 55 years later. The universe, apparently, really does build these things. But here's the thing. Almost no physicist alive actually believes there's a literal point of infinite density sitting at the center of a black hole. Infinity, in physics, is not an answer. It's an error message. When your equations spit out infinity, it doesn't mean you found something infinitely dense. It means your theory has walked off the edge of what it can describe and kept walking. So the singularity isn't really a thing hiding inside a black hole. It's the exact spot where our best theory of gravity commits suicide. Everything else on this list, every other idea we're going to talk about, is a different attempt to answer one question. If it's not a singularity, then what is it? And the strange part is that the man who first wrote down the equation for a spinning black hole, Roy Kerr, is now in his late 80s, and he spent part of 2023 publishing a paper arguing that the standard proofs don't actually show a real singularity forms at all. 60 years in, the people who built this idea are still arguing about what's at the bottom. We built a perfect mathematical monster. And then we spent 60 years trying to figure out if it's even there. Number 9. Space and time trade places. Before we can talk about what's inside, we have to deal with something deeply weird about the inside itself. Because when you cross the event horizon of a black hole, the thing that breaks isn't just your body. It's the meaning of the words here and later. Out here, where you are right now, space and time behave the way you expect. You can move left, right, forward, back. You can stand still in space. But time you cannot stop. It drags you forward, 1 second per second, whether you like it or not. You have freedom in space. You have no freedom in time. Cross the horizon of a black hole, and those two swap. Inside, the direction pointing toward the center, toward the singularity, stops behaving like a direction in space. It starts behaving like time, which means falling toward the center is no longer something you're doing. It's something happening to you, as unavoidable as tomorrow. You cannot fire your engines and hover. You cannot turn around. There is no thrust powerful enough, because away from the center is now a direction in time, and it points backward into the past. You might as well try to rocket your way back to last Tuesday. Sit with that. Inside a black hole, the singularity isn't a place at the middle of a region. It's a moment in your future. The event horizon you crossed, that becomes a moment in your past. You didn't enter a room. You entered an appointment. Which does something quietly horrifying to the whole question we're asking. When people ask, what does the center of a black hole look like? They're picturing a destination. A place you could point a flashlight at, but you can't point at next Tuesday. You can only arrive at it. The center of a black hole isn't somewhere. It's somewhen. Now, physicists will add a caveat here, and it's a fair one. A lot of this space and time swap language depends on the particular coordinates you use to map the black hole. And coordinates are just labels we paint onto reality, like lines of longitude. Change the map, and the swap looks different. But the thing underneath the map doesn't change. Underneath all the coordinate choices is a hard, coordinate-free fact. Every possible path inside the horizon ends. Not ends badly. Ends. The road you're on has a final point, and there is no version of the map where it doesn't. You don't fall into a black hole. You fall into the end of your own timeline, and it's already been written. Number 8. The inner horizon and mass inflation. So far, we've been talking about the simplest kind of black hole. One that isn't spinning, isn't charged, just a plain sphere. But those don't really exist. Every real black hole in the universe is spinning, usually ferociously. And spinning black holes have a second horizon, hidden inside the first one. A horizon within a horizon. It's called the Cauchy horizon, and it is one of the most dangerous surfaces in physics. To understand why, you need one idea. Blue shift. When light falls into a gravity well, it gains energy. It gets bluer, hotter, more violent. Now imagine light and matter that fell in long ago, and light and matter that's falling in now, all piling up against this inner horizon at once, from opposite directions, at effectively the speed of light. They don't just collide, they amplify. In 1968, Penrose, him again, pointed out that anyone reaching this inner horizon would see the entire outside universe blue shifted toward infinite energy. The whole future of everything, compressed and slammed into a single blinding sheet. Then, in 1990, two physicists named Eric Poisson and Werner Israel worked out what that actually does. And they gave it a name that sounds like a threat, because it is one. Mass inflation. Here's what happens. As those two streams of radiation counterstream past each other at the inner horizon, the effective mass of the interior doesn't just increase, it explodes. Exponentially, run away, screaming upward. The density climbs toward infinity. The curvature climbs toward infinity. In a fraction of a second, a growing wall of energy assembles itself out of the light of the entire history that ever fell in. This isn't a point singularity like the classical picture. It's a sheet, a null singularity, a wall of infinite curvature that builds itself from the accumulated past of the black hole. Everything that ever fell in focused into a single lethal surface, waiting. And now, here's the cruel little joke the universe plays. Remember, this inner horizon of a spinning black hole is also, as we'll see, the doorway. The place where the geometry supposedly opens up into other regions, other universes, tunnels out. It's the interesting part. The part that might let you through. Mass inflation is the reason you probably can't use it. The same structure that promises you a passage is the structure that builds a wall of blue-shifted fire across the entrance. The door and the thing sealing the door are the same object. Physicists still argue about how bad it really is. Quantum effects might soften that wall, blur it, make it survivable in some exotic sense. But the mainstream reading is stark. Whatever tunnels, whatever doorways, whatever escape routes the equations of a spinning black hole seem to offer, mass inflation is the bouncer standing in front of all of them. The inside of a black hole isn't just a grave. It's a grave that remembers every single thing that ever fell in, and it keeps all of it pressed flat against a wall of light, forever. Number 7. The fuzzball. Everything we've said so far assumes there's an inside at all, a region, a volume you could, in principle, fall through. String theory looks at all of it and says, what if there isn't? This is the fuzzball, and it comes mostly from one stubborn, brilliant physicist named Samir Mather at Ohio State, who has spent decades arguing that the entire mental image of a black hole is wrong. Here's the standard picture we've been using. A black hole is mostly empty space. There's an event horizon, an invisible surface, nothing special to touch. You'd sail right through it. And then a long fall to a singularity at the center. Empty, empty, empty. Then a point of doom. That's the classic view. Mather says no. In string theory, when you actually try to build a black hole out of the fundamental objects, the strings, the higher dimensional membranes, you don't get empty space with a point at the middle. You get a tangled, vibrating, horizon-sized ball of stringy stuff. Solid, in a sense, all the way out to the surface. The space doesn't continue down to a singularity. It caps off, smoothly, right about where the event horizon would have been. There is no inside. There's just the fuzzball, and then the edge of it. The name is almost too cute for how radical the idea is, but fuzzball captures it. Instead of a sharp horizon wrapped around emptiness, you have a fuzzy quantum surface with no clean boundary and nothing hollow behind it. And this fixes some deep problems. The information paradox, the decades-old nightmare about whether black holes destroy information and break the laws of physics, largely evaporates because there's no singularity to swallow information and no smooth horizon to hide it behind. Every scrap of what fell in is still encoded in the specific vibrations of the strings on the surface. Nothing is lost. It's all just fuzz. Now here's the part that should make the back of your neck prickle. From the outside, a fuzzball looks almost exactly like a normal black hole. Same gravity, same shadow, same bending of light. The difference only shows up right at the surface, and only if you look with instruments we don't quite have yet. Which means when you look at that famous image, the orange ring, the black center, the first photograph of a black hole, you might not be looking at a hole at all. You might be looking at the surface of an object, a vast, tangled ball of strings the size of a solar system, wearing the face of a bottomless pit. We name them holes. We may have been staring at something that was never empty for a single moment. Number 6. The gravastar. The fuzzball says there's no inside. This next idea says there's an inside, but it's the last thing you'd ever guess. It's made of dark energy. And it might mean black holes, as we imagine them, don't exist at all. In 2001, two physicists, Pavel Mazur and Emil Motola, proposed something they called a gravastar. The name is a mashup, gravitational vacuum star. And the idea is that when a massive star collapses, it doesn't quite finish the job. It doesn't punch through to form a horizon and a singularity. Instead, right at the last moment, right at the edge where the event horizon would form, the collapse freezes. Something stops it. That something is a phase change in the vacuum itself. Think of water turning to ice. Same stuff, radically different behavior. In a gravastar, the vacuum inside the star transitions into a different state, one with negative pressure. And negative pressure, gravitationally, pushes out. It's the same weird property we attribute to dark energy, the stuff accelerating the expansion of the entire universe. So the interior of a gravastar isn't a singularity. It isn't even ordinary matter. It's a bubble of dark energy, held in, pushing outward, balanced against gravity's inward crush. Wrapped around it is a thin, incredibly stiff shell of ultra-dense material, the crust where the two forces meet. And outside that shell, from a distance, The gravity looks identical to a black hole's. You could orbit it and never know. Let that composition really land. The engine that's blowing the universe apart. The mysterious dark energy stretching galaxies away from each other faster and faster. A gravastar says a pocket of that exact thing is sealed inside a dead star, holding the corpse open from within. A little sample of the universe's expansion, bottled, at the center of what we thought was a hole. No singularity, no information paradox, no event horizon of no return. Just a strange, taut, glowing bubble that happens to bend light the way a black hole would. The catch, and it's a real one, is that nobody knows how a star would actually pull this off. What natural process freezes the collapse at exactly the right instant? And when black holes crash together and ring like bells, the gravitational waves we've caught with LIGO so far match plain old boring black holes pretty well. Not proof, but pressure. The gravastar is running out of room to hide. Still, every time we call them black holes, we're making an assumption. And Mazur and Motola's quiet suggestion is that we might have been holding a funeral for a star that never actually died. Number 5. The Planck star. Let's go back to the collapse itself and ask the question quantum gravity has been circling for years. When matter falls inward and crushes down toward that forbidden point, is there anything that can stop it? Any pressure, any force, strong enough to say no? In 2014, Carlo Rovelli and Francesca Vidotto said yes, and they called the thing at the center a Planck star. Here's the intuition. Everything in our experience that resists being crushed does so with some force. Electrons refuse to overlap, and that holds up white dwarfs. Neutrons jam together, and that holds up neutron stars. Each of these has a breaking point, and past it, gravity wins and the collapse continues. The classical story is that there's nothing left after neutrons. So the fall goes all the way to a singularity. But Rovelli and Vidotto work in loop quantum gravity, a theory where space itself is not smooth. Zoom in far enough, and space is grainy, quantized, made of discrete chunks, and you cannot squeeze matter smaller than the grain of space itself. As you approach that ultimate density, the Planck density, a number so large it barely means anything, the density where quantum gravity takes over, a new kind of pressure appears, a repulsion that comes straight out of the uncertainty principle. Space itself pushes back, so the collapse stops, not at a point, at an object, unbelievably small, unbelievably dense, but finite, a Planck star. And here's the detail that makes it clever. The trigger isn't size, it's density. The star stops collapsing when it hits Planck density, and a lot of mass at that density can still be much, much bigger than the Planck length. So the Planck star hiding inside a black hole isn't necessarily a subatomic speck. It could be a genuine object, sitting there at the core, held up by the graininess of space. There's just one more twist, and it's a beautiful one. From the star's own point of view, this whole process, collapse, freeze, and what comes next, is fast. But from our point of view, out here, time near that core is dilated, almost to a standstill. So the Planck star is, in a real sense, frozen. Caught in the middle of an event that, for it, takes an instant, and for us takes longer than the age of the universe. There's something hiding at the center of every black hole, this theory says. Not a singularity. A star. Paused, mid-motion, waiting for a clock that barely ticks. And it is not waiting to sit there forever. It's waiting to move. Number 4. The bounce into a white hole. So the Planck star is frozen at the center, held up by quantum gravity, caught in the slowest instant in the universe. The obvious question is, an instant of what? What is it in the middle of doing? Rovelli, working with Hal Haggard in 2014, gave an answer that is genuinely hard to hold in your head. It's bouncing. And when it finishes bouncing, the black hole turns into its own opposite, a white hole. A white hole is a black hole run backwards in time. Take everything a black hole does and reverse the film. A black hole is a region nothing can leave. A white hole is a region nothing can enter. And everything must eventually leave. Where a black hole pulls in and hides, a white hole pushes out and reveals. For decades, white holes were treated as a mathematical curiosity, a solution to Einstein's equations that surely nothing in reality corresponds to. Haggard and Ravelli said, "What if a black hole and a white hole are the same object, just at different stages of a single, enormous bounce?" Matter falls in. It collapses toward the center. It hits the Planck star, the quantum gravity floor, and it rebounds. The whole geometry tunnels, quantum mechanically, from the collapsing black phase into the exploding white phase. And out it all comes again. They nicknamed it black hole fireworks. Now, if this were quick, we'd have noticed. Black holes would be popping like flashbulbs across the sky. So why don't we see it? Time dilation. Again. The bounce is almost instantaneous for the matter at the core, but stretched across the outside universe, it takes an astronomically long time. For a black hole with the mass of a collapsed star, the rebound could take around 14 billion years. 14 billion years. That number should sound familiar. That's roughly the age of the universe, which means the very first black holes. The small primordial ones that some theories say formed in the chaos right after the Big Bang, could be reaching the end of their bounce right about now. Detonating. Somewhere out there, on this reading, the oldest black holes in existence might be finishing a 14 billion year explosion, and we might be able to catch the flash. So the interior of a black hole, in this picture, isn't a tomb. It's a spring under tension. Everything that ever fell in isn't gone. It's paused at the bottom of the deepest well in physics, on its way back up. The universe doesn't keep what it swallows. It just takes an incomprehensibly long time to give it back. You are not looking at a place where things end. You're looking at the slowest rebound in creation, halfway through. Number 3. Bigger on the inside. I want you to picture a black hole, a real one, at the center of a galaxy. From the outside, you can measure it. Its horizon has a definite size, a surface area you could, in principle, wrap a number around. For the black hole at the center of our own galaxy, that surface is a sphere, maybe the size of a large star's orbit. Big, but finite. Knowable. Now, how much space is inside that surface? Your instinct says, well, it's a sphere, so some finite amount. The volume of a ball that size. That's the intuitive answer. And in 2015, 2 physicists named Marios Christodoulou and Carlo Rovelli showed that the intuitive answer is catastrophically, wonderfully wrong. The problem is that the volume inside is a slippery thing in a black hole. Because, remember item 9, space and time are tangled up in there. When you actually do the calculation carefully, asking how much room is genuinely enclosed by that horizon, you don't get the tidy volume of a ball. You get something enormous. And worse, or better, it grows. The longer the black hole has existed, the more volume is packed inside it. The interior keeps inflating with time, even while the surface stays exactly the same size. Here's the number that broke my brain when I first read it. For a black hole, like the one at the center of the Milky Way, the interior volume, right now, is enough to hold something on the order of 1 million solar systems. And it's still growing. Given enough time, the volume enclosed by that unchanging surface tends toward infinity. Read that again. A finite surface. Fixed size. And behind it, an interior larger than you could ever justify from the outside, expanding quietly. Forever. Physicists sometimes call this kind of geometry A bag of gold. A tiny opening. The neck of the bag. And behind it, a space vastly larger than the neck has any right to contain. A black hole is the ultimate version. A modest, dark circle in the sky. And behind it, room for a universe. Rooms behind rooms. More added every second. None of it ever visible from where you stand. There's a fair objection. Volume inside a black hole depends a little on how you slice up that warped space-time, and Christodoulou and Rovelli made one careful, sensible choice. It's not the only possible one, but it's a good one, and the result is real. The inside of a black hole is not small. The inside of a black hole is, in a very concrete sense, one of the largest things in existence, hidden behind one of the smallest doors. You could hold the doorway in the palm of your hand. You could never, ever fill the room. Number 2, the Kerr ring and the doorway. We keep coming back to a spinning black hole, and now we finally have to face what's actually at the center of one. Because it is not a point. It never was. In 1963, a New Zealand mathematician named Roy Kerr did something people had failed at for nearly half a century. He found the exact solution to Einstein's equations for a rotating black hole. Not an approximation, the real thing. And since every black hole in the universe spins, the Kerr solution isn't some special case. It's the description of essentially every black hole that exists. And at the center of a Kerr black hole, the singularity is not a dot. It's a ring. Spin smears the point out into a circle. A ring of infinite curvature, spinning, with a radius set by how fast the hole rotates. A ringularity, some people call it. And a ring has a hole in the middle, which raises a question that has kept physicists up at night for 60 years. What happens if you go through it? According to the mathematics of the Kerr solution, and I want to be careful, this is the idealized, clean equation. If you pass through the disk bounded by that ring without touching the ring itself, you don't hit anything. You come out somewhere else. The geometry continues into a region that mathematicians describe with a negative radius, a place sometimes called the antiverse. And in that region, gravity from the ring is repulsive. It pushes instead of pulls. Some versions describe it as passing into another universe entirely, a whole separate space-time, reachable only by threading the needle through a spinning ring of broken physics. A door, an actual door, sitting at the center of the most common kind of black hole in the cosmos, mathematically opening onto somewhere else. And you already know why you probably can't walk through it. Item 8. That inner horizon you'd have to cross to reach the ring is exactly where mass inflation builds its wall of blue-shifted fire out of the black hole's entire past. The pristine tunnel exists in the clean equation. Load in a realistic universe. Real infalling light. Real history. And the passage tends to seal itself behind a sheet of lethal energy. Roy Kerr himself, 6 decades after writing the solution, has argued the true singularity might not even form the way the textbooks insist. So here's where that leaves us. At the heart of nearly every black hole, the math draws a ring, and through the ring, a doorway to another place. It might be a real feature of reality. It might be a ghost that only exists in the idealized equation. We are not sure. 60 years on, we are genuinely not sure whether the universe put a door at the bottom of every black hole, or just a very convincing picture of one. And the only way to find out is to go through, which is the one experiment nobody comes back from. Number 1. The end of time. We've spent this whole countdown asking what object is hiding inside a black hole. A point? A ring? A star? A bubble of dark energy? A ball of strings? And every one of those answers is really a guess about the same thing. a guess about what happens at the place where our physics gives out. But there's a final answer, and it's not an object at all. The thing hiding inside a black hole might be the end of time. Start with what we know for certain, the part no theory disputes. Once you cross the horizon, your future is finite. Not your future in space, your future period. Every path you could take, every choice, every desperate maneuver terminates. Physicists have a cold, precise phrase for this. They say the world lines are incomplete. Your timeline, the sequence of moments that make up your existence, does not go on forever and does not loop. It stops. There is a last moment, and after it, there is no after. Out here, we've never met such a thing. Time, for us, always has a next. Ask, what happens next? Anywhere in the ordinary universe, and there's an answer, even if the answer is just empty space and cold. Inside a black hole, you reach a place where the question, what happens next, has no answer. Not an unknown answer. No answer. The road doesn't go anywhere because the road is over. And there's a haunting image people love here. The idea that as you fall in, you'd look back out and watch the entire future of the universe play out above you. Stars being born and dying. Galaxies winding down. All of cosmic history fast-forwarding in the shrinking circle of sky behind you. I have to be honest with you, because this channel is about what's true, not just what sounds good. For a simple fall into a simple black hole, that particular image is mostly a myth. You don't get the grand slideshow on the way down. But, and here's the real version, the one that's actually stranger. There's a place inside a spinning black hole where something like it does happen. At that inner horizon, the one from item 8, an observer really would see the outside universe blue shifted, sped up, its whole future compressed and rushing toward them at once. The catch is that this is the same surface where mass inflation builds its wall. So the universe seems to offer you a seat to watch all of time unfold. And then it detonates the theater around you at the exact moment the show would begin. Pull all the way back and look at what a black hole really is. It's a place where the future runs out. We spend our entire lives unable to imagine our own ending, unable to picture a last moment with genuinely nothing after it. And the universe went ahead and built that exact thing, millions of times over, and scattered them across every galaxy. Regions where tomorrow simply stops being available. Maybe there's a ring down there. Maybe a Planck star, frozen mid-bounce. Maybe a ball of strings that was never hollow at all. We don't know. We may never know, because the one place that holds the answer is the one place from which no answer can ever climb back out. But whatever object sits at the bottom, it sits at the end of time. And there is something almost comforting in that, if you let it be. The universe is not infinite in every direction. It has edges. It has places where even time politely stops. And for all our fear of these things, these dark, silent, patient holes in the sky, maybe what they really are is the universe's quiet way of proving that everything, absolutely everything, eventually comes to rest. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.